This episode is sponsored by Audible. A human floating around outside Earth's gravity is very much a fish out of water, but our distant ancestors were literally fish out of water, and they adapted to living on land pretty well. Maybe some of our descendants will adapt just as well to life without gravity. Last February, we did a well-received episode on low-gravity planets and the probable effects on human physiology and evolution. We also talked about how close to the truth science fiction has come in its portrayals, so taking that concept all the way to zero-G or neo-zero-G seemed like an appropriate follow-up. Of course, we'll be talking mostly about man-made habitats in this episode because to hold an atmosphere in place requires either significant gravity or an airtight enclosure, but we will talk about some other possibilities. And while this won't be a very heavy episode, you might still want to get a sealed drink and a non-crumbling snack and seatbelt yourself in for a while. The terms neo-zero-G, micro-G, and microgravity are all interchangeable terms for the same thing. What astronauts experience in space used to popularly be called zero-G, but that was a popular misnomer, because there's a solar system and a universe around us that makes it impossible to get away from all gravity. If you're in a circular orbit around the Earth, centrifugal force cancels the Earth's gravity, but the Sun still exerts about 0.5 of a G on you and your spacecraft, and the Moon exerts about 3/millionths of a G. Your craft, crew, and cargo all have mass and so also exert some attractive force on each other. An average-sized adult close enough to shake hands with exerts about 1/billionth of a G on you, and if you're the length of the International Space Station away from the center of the International Space Station, it's also exerting about 1/billionth of a G on you. For objects that are very close, tidal forces also become a concern. The strength of gravitational force is inversely proportional to the square of the distance, so there's slightly less gravity on your head than your feet here on Earth, but we can usually ignore that. In microgravity, less so. The very slight gravitational force exerted on you by the astronaut you're shaking hands with is several times stronger on your hand than on your shoulder. Differences can have a measurable effect, for example, on current ISS experiments on microassembly and microcrystal growth. You can mostly isolate an experiment from all the jostling and vibration caused by astronauts bumping around in the space station, but there is no insulating it from their gravity and tides. So, while the term zero-G was close enough decades ago, more precise measurements on more sensitive modern experiments requires us to adopt more precise terminology. Human bodies are not very well equipped to adjust or adapt to microgravity, and I think that's largely because evolution has never, in all of life's history on Earth, had to deal with any changes in gravity. The temperature, light level, day length, oxygen levels, and most everything else about every natural habitat vary significantly with the season, location, and geological era. Gravity has been the one near-absolute constant. 1G is by definition 9.80665 meters per second, meaning that the speed of a falling object, absent air resistance, will increase by 9.8 meters per second every second. This value is an estimate of the average gravity on the Earth's surface, but local gravity varies over the Earth's surface by less than 1%, from 0.995 G atop mountains near the equator to a crushing 1.003 G over the Arctic Ocean, the place where the Earth's surface is closest to the Earth's core. The gravity we experience today was the same for our primate ancestors, our rodent, reptile, fish, and bacteria ancestors, and every living thing that's ever lived on this planet along the way. So to call a human experiencing microgravity a fish out of water is just about the most apt figurative use of that phrase I can think of. Taken out of the environment they evolved to function in, our bodies start to malfunction, and sometimes rather badly. Even extraordinarily fit and healthy individuals, like those selected to become astronauts, such as Chris Hadfield or Scott Kelly, end up having serious medical issues arise from extended stays in microgravity, some of which can jeopardize the mission, and some of which don't go away when the astronauts return to Earth. We will have to solve or at least address all of those problems before we dare send humans much farther from Earth than we already have, at least without artificial gravity. The first common problems that arise are nausea and headache. The first minutes in microgravity can be rather like car sickness or seasickness. The vestibular system of your inner ear uses fluid flowing freely in your semicircular canals to sense acceleration and determine what direction down is in. Your brain attempts to reconcile the orientation you sense with what you see, and just like when you're in the cabin of a rocking boat or reading in a moving car, your brain can't do that reconciling, but it keeps trying, and eventually it notifies you that something is wrong here by making you feel as awful as possible. There's a reason the training plane NASA uses to simulate microgravity has been nicknamed the Vomit Comet. The failure of bodily fluids to move normally is a big problem when your body is 60% water. Long ago, astronaut Wally Schirra explained in commercials for decongestants that sizes do not drain in space, so when he gave his fellow crew members on the Apollo 7 mission his cold, they were in real physical pain for days and just had to walk through it. Wally also invited us to imagine what it would be like to sneeze inside a space helmet, but I won't do that in case you're enjoying that snack I recommended earlier. And it's one of many examples of how normal human bodily functions aren't normal in spacesuits or microgravity. Cerebrospinal fluid also does not move around in microgravity the way your body needs it to. Without gravity pulling it down, it pulls in your head and exerts pressure on your brain and the backs of your eyeballs. This contributes to the headaches and also deforms the eyeballs a bit. Astronauts are screened for having perfect vision, but after several weeks on missions, they often end up with blurry vision and nearsightedness that doesn't always go away when they return to Earth. Worse, the adjustable focus glasses that NASA issues are so uncool looking that they somehow manage to make even astronauts look uncool. Blood flow is a more serious issue though. Your blood doesn't rush to your head in micro-G like when you hang upside down, but also doesn't drain downward like normal. That's why astronaut faces always look a bit puffy during missions. Then after we get used to seeing them like that, they look a bit gaunt doing interviews back on Earth. They also say they get skinny bird legs in space because blood and interstitial fluid do not pool down like they normally do. But these are not just aesthetic concerns, they are indicators of blood not flowing through the body normally, which means the heart isn't functioning normally either. Blood pressure and heart rate also drop in micro-G, and this is where things get truly dangerous. Without gravity to overcome, your heart simply does not pump as hard. When astronauts are walking lightly, their heart rates are about the same as when they are lying in bed on Earth. When the heart does not work as hard, it atrophies, losing strength and soon thereafter losing muscle mass. This condition gets especially concerning when astronauts return to Earth, because the heart must regain that muscle mass before it can adjust the new, heavier load. Many astronauts have passed out on re-entry after a long mission, and several have ended up having to ingest a lot of salt or take low blood pressure medications for many months after their missions. And your heart is not the only muscle that atrophies quickly in microgravity. It probably will not surprise anyone that when your body doesn't have to exert itself to lift things or lift itself, it gets weaker, but it is the posterior muscles, the core muscles that stabilize your back, abdomen, and pelvis, that atrophy the most quickly because they're composed mainly of slow-twitch fibers. Exercise helps a great deal, so astronauts spend 2 hours a day working out, but it seems to only slow the atrophy, not stop it. Atrophy of the muscles that hold the body stable and erect cause another host of problems when astronauts return abruptly to full gravity on Earth. We do not currently have any moon bases or low-G rotating space habitats where astronauts can return to gravity gradually, but as more people spend longer in microgravity, such facilities will almost certainly become necessary. This is where rotating habitats like O'Neill cylinders or the Kaplan 1 space habitat would be ideal, because the simulated gravity you experience inside one is proportional to your distance from the hub. So if it's a bit too heavy for you today, you just have to move up a floor to where the gravity is lighter. Your bones also deteriorate in space. When load-bearing bones aren't under any load, they quickly start losing calcium, which makes them brittle. This happens even to earthbound people who don't exercise much, but in microgravity the effect is more rapid. And calcium released from your bones gets absorbed into your blood and passed through your kidneys, where it can form the jagged variety of kidney stones, which are extremely painful and debilitating. Staying very well hydrated reduces but does not eliminate the kidney stone problem. And just like with muscle atrophy, exercising 2 hours a day, particularly exercise with some impact like running on a treadmill, reduces but does not eliminate the bone deterioration. I suspect by now it is pretty clear why I so often emphasize the importance of spin gravity rotating habitats in space settlement. But as serious as these issues are, they are clearly manageable and recoverable. In 1994 to 1995, Valery Polyakov spent a continuous 437 days or 14 months aboard the Mir space station. He's now 77 and still in good health according to the Russian Space Agency. Gennady Padalka spent a lifetime total of 879 days or 28 months in microgravity, spread over 17 years and 5 missions aboard Mir and the ISS. His career demonstrates that it's not only possible to recover normal health after months in microgravity, it's possible to remain fit enough for the space program so you can do it all again. But of course we have to remember that astronauts are not ordinary people. They are among the most extraordinarily fit and healthy specimens their respective countries could find. So there's no data on how average or out of shape folks will fail in space or recover from it, and I doubt NASA is going to run an experiment anytime soon, though my fingers are crossed. And of course the late great John Glenn, first American to orbit Earth and longtime senator from my own state of Ohio, did manage to get back up into space again at age 77 in a NASA experiment focused on the effects of the environment on seniors. So there is hope for those who want to get into space as a test subject for how microgravity affects folks who aren't in peak health. And we do need to know those eventually, since space settlement is not intended to rely on sending only Olympic athletes to space. The physiological effects of extended microgravity are a major concern for planning any manned journey to Mars. Realistic mission plans put the astronaut in transit for at least 18 months. The landing party would certainly have an easier time adjusting to 1/3 G on Mars' surface than adjusting abruptly back to a full 1 G, but they wouldn't have the help of a dedicated ground crew and medical personnel around them, only each other. And then after months in Mars 1/3 G, they'll spend another at least 18 months traveling back to Earth. For a deeper analysis of the gravity-related issues our explorers and their children might encounter on Mars, you can check out our episode on low-gravity planets. But barring any sudden medical breakthroughs that solve all of the microgravity problems, we'll have to equip the spaceship with a rotating section to travel in, what we often call the drum. Such a drum would add enormous fuel costs and construction time to the mission. The drum would have to be quite large if the astronauts were supposed to spend any significant time in it. As I mentioned, centrifugal force is proportional to the distance from the axis, so a person standing inside a drum feels literally lightheaded, with lighter simulated gravity on their head than their feet. The only way to remedy this is to make the drum so large their height is pretty small compared to the radius. For example, if the radius is twice your height, your head would feel half as much gravity as your feet. But if the radius is 10 times your height, your head would feel 90% as much gravity as your feet, a big improvement at quite a cost. And the more surface area the habitat has, the more massive shielding it needs. When people and cargoes move back and forth between the rotating and non-rotating sections, they carry and transfer their angular momentum, so you'll need thrusters and flywheels to keep the respective sections rotating or not rotating correctly and steadily, otherwise your whole vessel will be spinning before long. Maneuvering also gets complicated when you're carrying a massive gyroscope around, an issue you either deal with or solve by having a second giant gyroscope rotating the opposite direction. This is turning into quite a lot of mass we're adding to our vehicle that we currently have to lift into orbit with rockets at about $10,000 a kilogram, and this is the answer to a question I frequently get about why the ISS just doesn't have a rotating drum section. I mentioned earlier that the worst problems associated with prolonged microgravity arise when the astronauts return to Earth, so simply not returning to Earth is an obvious way to solve those problems. This has actually been proposed, non-jokingly, as a way to solve a lot of the problems of the Mars mission. Just skip the brief jaunts, cautious visits, and hurry along a return vehicle. Just make the trip one way and commit to a colony outpost founded by people prepared to spend the rest of their lives there, paving the way for the future arrivals. So it's not completely unreasonable to think this might be a solution to the problems caused by returning from microgravity, particularly if someone had been stuck in space for longer than planned and found they were medically unable to return. In the early 90s, cosmonaut Sergei Krikalev was stranded aboard the Mir space station not because of any technical problem, but because his home country, the Soviet Union, dissolved. Even his intended landing site at the Soviet Cosmodrome was suddenly in a different country, Kazakhstan. So he ended up staying aboard Mir for 311 days, twice what had been scheduled. Sergei was alright and even flew several other space missions, but his case does raise the question of what would happen if someone were stuck in space for much longer. Every improbable event will happen eventually if you wait long enough, so it's fair to say that someday, either by accident in space or disaster on Earth, someone is going to get stranded in microgravity for so long they can't ever return to full gravity. That would be a terribly lonely existence if that person or crew were stranded on the only space station in orbit, but it might not be so terrible if it happened in an era where there's significant infrastructure and permanent human presence in orbit. Then they'd at least have company and a job where they'll always be the most experienced worker around. Though unless others are remaining permanently, it might be rather rough on them having many short-term relationships always ending in remaining in touch by correspondence or not at all. That may incline many folks who work for long times in space to opt for more expensive options, allowing them to return to gravity eventually, like a space miner having a rotating section on their ship or taking long vacations into gravity. Of course, it's also very possible that before we build major orbital infrastructure, we'll establish a permanent presence on the moon. In fact, we'd probably establish lunar mines and factories precisely to build our low-orbit infrastructure, and those lunar colonies might be viable places to send our stuck astronauts to, either to retire or to recover more gradually, where they only have to adjust abruptly to 1/6G, which is probably a lot easier than adjusting to an abrupt return to full 1G. And by the way, the idea of retirement homes in space has also been kicked around, a place where less physically able people can enjoy mobility again, where weak bones and muscles don't matter so much, and where there's zero danger of falling in the shower. Though we should also remember that while many might find those attractive options now, they may be redundant in a century as medical technology is also likely to improve. So now that we've covered involuntary permanent residency and microgravity, let's think about voluntary stays. We take it more or less as a given on this channel that someday people will live on Mars, the Moon, and Venus. If people live their lives there, they will adapt, and there's really no need to ensure they're able to return to 1G. Most Americans have never visited the countries their ancestors lived in 200 years ago, and most humans have never felt the need to visit East African grasslands where our species originated, so there's no reason to think most Martians or Venusians will visit Earth ever. And with options like virtual reality available for visits, there's less need to make sure they physically can visit. The same is true for people who will be farther out mining asteroids and comets. If you work in space, you'll probably be in microgravity all day long and quite accustomed to it. Your spaceship or mining facility might have a habitation drum providing gravity, but that represents an extra cost and maintenance issue, so wouldn't be a feature for a marginal operation, and most businesses usually are marginal operations to some degree, though spin gravity habitats on facilities might also be something government mandated. So too, full gravity is harder than low gravity, so spaceships in smaller facilities might feature Martian or lunar levels rather than Earth standard gravity. It might seem a major inconvenience to have to return to the 1G O'Neill habitat for a few months every year, just to keep medically able to return to a planet you don't care much about, and it certainly will be inconvenient having to either travel great distances to that habitat or drag such a habitat around with you, paying for it all the way. If colonizing the solar system plays out like settlement of the American West, or like is depicted on The Expanse, the first settlers in some areas might be people acting on their own, either poor enough or enterprising enough to set off and try to make a life or a fortune grabbing up those resources that are out there for the taking. Folks like those are likely to skip the time and expense of building rotating sections for gravity, let alone giant O'Neill cylinders, so you'll have humans living and working in microgravity for years with no illusions about returning to Earth. If they find they can adjust to that life, it is likely many will just go on that way, one job to the next. It seems inevitable that many spacewalkers will simply become permanent microgravity residents. Of course, if you are talking about a civilization or nation of people living permanently in microgravity, they'll have to be able to reproduce, and we still don't know if this is harder in zero gravity. While animal embryos and pregnant animals have been sent into space, there hasn't been a complete animal gestation in space, where the animals got pregnant in space and remained there until they gave birth, let alone multi-generational studies, so the data on this is lacking and is totally absent where humans are concerned. Animal data won't necessarily tell us if humans can have normal and healthy births in space. We already gestate and give birth rather differently than other mammals, owing to our torsos being vertical and our pelvic canals being relatively small to keep our guts from falling through, and if microgravity affects the flow and pooling of blood, that will have effects on a pregnancy. This is probably manageable, but the rigorous scientific answer to whether or not human beings could actually breed in space is, we don't know, no one has tried. I've talked so far about the many problems of adapting and adjusting to microgravity, but I am very much a science optimist, and I tend to believe that none of these are absolute barriers, only problems to work through. We've done episodes on genetic engineering, cybernetic enhancement, and all sorts of ways we might alter our bodies and minds, So problems like bone and muscle atrophy and abnormal fluid pooling seem pretty modest and very solvable, and what we treat initially with drugs or mechanical enhancement we might eventually address with permanent genetic graft so that workers will simply be born able to remain in microgravity indefinitely. Indeed, this is the root of the term cyborg or cybernetic organism. The word originally meant the various biological and chemical adaptations or treatments we might need to make life in an off-Earth environment possible. The concept of a cyborg as someone walking around on mechanical limbs or sporting metallic augmentations is a more modern development. That version might be in the cards too, and in many cases folks might embrace chemical, genetic, surgical, or mechanical alterations, treatments, or augmentations that made their life in a specific non-Earth environment easier. Chances are, space-dwelling humans will live in many different levels of gravity and even move around between them. If you colonize a planet, you're pretty much stuck with whatever gravity was native to it. Even if you had something like artificial gravity generators, you presumably need power to run those and run them perpetually. Doing that planet-wide would seem a far greater effort than just adapting life to that lower gravity. The preferred human habitat though will likely be the O'Neill cylinder, and those can be constructed and spun up to synthesize however much gravity you'd like. There's no upkeep cost to that gravity beyond maintaining the structure itself, since it relies on conservation of angular momentum. It will keep spinning in a vacuum environment with no friction and generate spin gravity while it does so. But that gravity is not uniform, it is proportional to the distance from the axis of rotation, and unless your drum is very large, that difference can be rather noticeable in multi-story buildings or any landscaping that is more vertical than flat grasslands. The skyscrapers or even trees will be dealing with significant changes to gravity along their height in any drum not kilometers in diameter. Many would probably be a lot smaller too, just the tens of meters minimally necessary to avoid noticeable differences in gravity between your head and feet. It would seem a terrible waste of expensive living space if everyone just lived on that one level at the right radius to have exactly 1 G. The outer levels with higher gravity probably would not be favored as much as the lower G levels closer to the axis, but there's no good reason to leave either uninhabited. But the folks who live in microgravity won't have to go to the inconvenience of building a huge drum, making it strong enough not to spin apart and controlling its rate of spin. They pretty much just build a box of any convenient size and shape or even inflate a balloon, then slap on some radiation shielding, and they are ready to move in. This will give them quite an advantage when there's new territory to settle. They will also be able to handle long remote space missions, so they likely will be the vanguard exploring and surveying new systems, which would usually imply access to the choicest parts of those new territories. This means they will settle a lot of places the floor-bound folks haven't reached yet and might not ever reach. And this raises interesting possibilities for human evolution. When two groups are separated in this way, they will begin to diverge, socially, then culturally, then genetically. We might very well find human species branching into groups that find each other's way of living and the appearance of their bodies quite alien. There's no way we can know for certain if they'll call each other floaters or sinkers, so I'm forced to assume they will. Floaters living in microgravity will probably tend towards much lighter skeletons with scrawny limbs, as they tend to be portrayed in science fiction. One might also imagine they would adapt away from hands and feet towards 4 hands, their feet and toes shifting toward being able to grab things, as that would be more useful than the modern foot and leg structure, which has to handle lots of repeated heavy impacts. And while such a thing might take a long while to evolve naturally, it's not likely to be a major challenge for genetic engineering. Indeed, our entire bipedal setup is less advantageous in zero gravity too, where things like floors and walls and ceilings become rather arbitrary. You can swim and fly through air too, and while I'd imagine early space travelers might opt for clothing that let them push the air to move about, webbed fingers and toes might develop and even wings aren't off the table. A culture evolved, or engineered, for microgravity might be a pretty alien thing, shifting to more aquatic or avian formats. While that sounds alien to us, it might seem eccentric and reactionary to them that sinkers would migrate into space and then refuse to adapt to it. Micro-G is the norm, what you're going to find in most of space, with gravity only available on planets that might be habitable and in those inconvenient rotating cylinders. But when your subspecies simply adapts to the conditions in space, your options for places to inhabit are pretty much the definition of vast. We also have a host of megastructures focused on low or no gravity that we discuss here less than rotating drums because we tend to focus on Earth-like habitats. One of those is the gravity balloon. This is a structure where you just have a big balloon full of air, whose outer surface is covered with protective material. That might be armor and solar panels, or just rubble and spill from mining an asteroid, or ice or some sturdy transparent material if you want to see outside or let light in. Here the pressure of the air, presumably at one standard Earth atmosphere, is counteracted by the weight of the outer protective layer, thus not something that can pop from a puncture in spite of the implication from being called a balloon. Given that it's the air in the balloon generating that gravity, these can get to be enormous. One modest asteroid ground down to provide the protective outer layer might provide a culture's whole living area, potentially a whole world. Considerably larger than planets in fact, the atmosphere, a giant hollow empty steel shell, is several times larger than the Earth and filled with an Earth-like atmosphere. You can also have some rather unique biology in zero gravity, especially when we include low gravity of less than a percent human normal, floating islands held aloft by buoyancy, or trees and coral reefs stretching through kilometers of empty air. You would still have weather in such things even if its driving forces were quite different. Those might make for very attractive environments to visit and to live in, where you could fly or swim around the sky as easily as a fish, and you could arrange bubbles of water and land with some careful engineering. So returning to the fish out of water analogy for a moment, it's relevant to note that while humans out of gravity have similar problems, some fish do voluntarily venture out of the water when they have good reasons. Some found that laying eggs on the beach was a good way to keep them safe, and some of them spent so much time out of water their species evolved to land, and now they are driving cars, doing science, and watching videos on colonizing space. So it is worth pondering if our species' relationship with gravity could go the same way. Considering how much science fiction takes place in space, relatively little of it actually takes place in zero gravity, even in books where there is no need for expensive special effects to simulate it. And even when we do see it, it tends to be short scenes. Very few authors have tackled true microgravity cultures as a topic. One who did was Larry Niven in his 1984 novel Integral Trees, book 2 of his State trilogy, and its sequel Smoke Ring, which both take place in a thick gas halo around a neutron star in which life has evolved in a massive atmosphere halo around that star with no gravity. The story follows the descendants of a team of humans who arrived to explore it and now dwell in that microgravity environment, and Integral Trees is our Audible audiobook of the month. This is not Niven's first time winning our audiobook of the month, and with good reason. The author of Ringworld, The Mote in God's Eye, Lucifer's Hammer, A Word Out of Time, and many more excellent novels and short stories, writes science fiction that is simultaneously mind-blowingly fantastic and scientifically realistic, and you can find them all on Audible. Just visit audible.com/Isaac or text Isaac to 500-500. Audible has an incredible library of thousands of audiobooks, theatrical performances, original entertainment, guided fitness and meditation, sleep tracks, and podcasts, and now's the perfect time to join as they're having a President's Day sale for 6 months of Audible for just $9.95 a month. For a limited time, in addition to accessing one title from their premium selection, you can download and stream thousands of all-you-can-listen audiobooks, originals, and podcasts for less than the regular membership. Again, just visit the link in the episode description, audible.com/Isaac, or text Isaac to 500-500. Some of you probably noticed we had a few changes in our schedule, swapping this week's episode and last week's Colonizing Red Dwarfs on the schedule for January, and even moving around the monthly livestream Q&A, which appeared on the schedule for Sunday, January 24th and January 31st. I had forgotten that I had moved it to the 24th because my wife Sarah, who co-hosts the livestreams, was out of town for a wedding on the 31st, and figured I'd just forgotten January had 31 days and moved it back. I want to thank my longtime friend David Thomas for being nice enough to fill in for her this last weekend. I usually talk about our upcoming episodes at the end of a video, and we'll get to the schedule in a moment, but someone mentioned to me how they kept missing the live streams and they didn't realize they could watch them afterwards. The live streams have replays available, so if you missed that or last week's episode, Colonizing Red Dwarfs, you can still catch them. So today we looked at gravity, or rather civilizations existing in an absence of it, and next week our topic is going to be a substance we can only detect by its gravity, as it seems to be absent in every other respect, as we discuss dark matter, what it might be, and what technologies we might be able to develop for using it. After that, we have our mid-month bonus Sci-Fi Sunday episode, Multi-Species Civilizations and Co-Alien Habitats, on Sunday, February 14th. And in 2 weeks we'll be returning to the topic of space warfare to look at orbital bombardment, and we will finally find out what the first rule of warfare is. If you want alerts when those and other episodes come out, make sure to subscribe to the channel. And if you'd like to help support future episodes, you can donate to us on Patreon or our website, isaacarthur.net, which I'll link to the episode description below, along with all of our various social media forums, where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. You can also follow us on iTunes, SoundCloud, or Spotify to get our audio-only versions of the show. Until next time, thanks for watching, and have a great week.